Okay, so now we will learn another important function of solid state physics, that is called Fermi-Dirac distribution function. Okay, so normally we know already all these things. Normally in a metal there are two, if we talk in terms of energy level, so there will be a valence band and there will be conduction band. Okay, and in between that there is a slight overlap. There will be slight overlap between this conduction band and the valence band. Okay, so normally at 0 Kelvin the valence band, it will be filled with electrons and the conduction band, it will be empty. Okay, so at 0 Kelvin the maximum energy level available is called the Fermi energy. Okay, but once the absolute temperature of the metal is increased, then what will happen? The electron, it will be excited, and this it will go from lower energy to higher energy level. Okay, it will go. So this, how many electron it will occupy, or we can tell how many electrons it will go to the conduction band, or this occupancy, this probability distribution function is given by, actually this was derived by Fermi and Dirac, so that is written as, at any energy level the occupancy of the electron is, at any energy level, okay, it is 1 plus e to the power E minus EF, that is the Fermi energy, by kT. This K is Boltzmann constant, T is the absolute temperature. Okay, this is the Fermi-Dirac function. Okay, now as I told, now if we try to plot it, we will be trying to plot it. So this x-axis is my energy level, and my y-axis is the distribution, which is Fe. That means at any energy level at a given temperature, okay, how many electron, the occupancy of the electron, you can find out the probability. So now first talk about at t is equal to 0. At t is equal to 0 and the energy is above the Fermi energy. Okay, that means first we will consider t is equal to 0 and my E is equal to E greater than EF. Okay, so now this, as this is the x-axis is energy, so let this point it is EF, this is the Fermi energy. Now if E greater than EF, then E minus EF greater than 0. So this term is greater than 0. And T is something by 0, T is 0, something by 0, it is infinity. Okay? So 1 upon infinity. 1 upon infinity. That means this term is positive. Positive quantity by T is equal to 0. So something by 0 is infinity. E to the power infinity means infinity. Entire denominator become infinity. 1 by infinity is 0. So that means if the energy is higher than the Fermi energy and the absolute temperature of the metal is 0, then the occupancy is always 0. So it will be like this. Now let us consider for the same condition, if E, the energy level, is less than the Fermi energy. If it is like that, then this term is negative. So e to the power minus infinity. Okay, so e to the power minus infinity means what? So this term will come as, so this term, it will come as e to the power minus infinity. E to the power minus infinity means 1 by e to the power infinity. E to the power infinity means infinity, 1 by infinity means 0. So this term entirely it will vanish if t is equal to 0 and E less than EF. So 1 by 1 it will be remain as 1. So now for E less than EF means this portion, this side is less than EF, and if t is equal to 0 you will get this function. So this is your Fermi-Dirac function at absolute temperature for two separate cases. Okay, now if T is, now if the another condition is if T is greater than 0, that means say it is T1. Okay, so now in that case, suppose first we consider this is a positive quantity. Okay, it's a positive quantity, E greater than EF. So this is a positive quantity, everything it will be positive, some value we will get. So now in such case we will not get it as 0, it will be slight, it will be increasing like this. Okay, and similarly it will be not 0. Okay, and similarly if it is, if the value E is less than, if it is E less than EF, okay, means this side, this left side. So what will happen? This is a negative quantity, this is a negative quantity. So 1 by negative. So what I mean to say, this quantity, as earlier it was at t is equal to 0, it was 1. Now it will not remain 1, it will also it will reduce. So now the function you will get like this, green color. Okay. Now if we take another temperature T2 which is greater than T1, so what will happen? If we put, so now this quantity, whatever, because it is in denominator, temperature was in denominator, so if that denominator will increase, basically the entire thing it will, if it is increase, then this term will decrease. If this, now the entire denominator, if it is decreased, then finally this value will increase. So we will get further like this. Similarly, in opposite case, means if E less than EF, E less than EF, then what will happen? This term it will decrease, because here a negative sign is there, E less than EF. So that means it will further reduce like this. Okay. So now the function is like this. So suppose some other function T3, you can take T3 which is again greater than T2, so you will get not, sorry, here it will be not like this, so you will get the things like this. Okay. So now if we take another function T3, another temperature T3 which is still greater than T2, so you will get things like this. Okay. Got it? Now for any temperature, another thing, at any temperature which is greater than 0, but the energy level at Fermi energy, that means another condition if we create, say T is not equal to 0, T is not equal to 0, but the energy of the metal, it is at Fermi energy, that means E is equal to EF, then what should be the value of the distribution function? Because this is whatever may be, if T not equal to 0 but E is equal to EF, then this term is 0. So e to the power 0 is 1, so 1 plus 1 is 2, 1 by 2 means it is always, it will be in half. So your line it will be like this. So this is the now if we know the density of the state, and if we know the this electron occupancy from this distribution function at a given temperature and given energy level, then we can find out the number of electrons available there. Okay. So this is the importance and interpretation of Fermi-Dirac function. So I think you understood. Thank you so much.